Picture, if you will, a universe of stars, each with its own unique composition and story. Now imagine finding one star, Jade 0931, which holds within it a peculiar mystery that's challenging our understanding of cosmic history. This celestial body, formed in the primeval stages of the universe, offers us a glimpse into the cataclysmic events of the past, events that spewed enriched material into the cosmos, eventually giving birth to new generations of stars. However, J0931 is an oddity with an unusual composition that sets it apart from its stellar brethren. It's a tantalizing puzzle that we've just begun to unravel. But the key piece of this cosmic puzzle? Well, we'll get to that in due time. What's up, my amazing and curious folks? Ready for another journey into the realms of the unknown? I'm your host, Cesar, and joining me today is the ever-insightful Sonia. So, buckle up and hit that subscribe button because we're about to unravel another cosmic mystery together.
Hi everyone, can't wait to dive into this cosmic journey with you all. Get ready to have your minds blown.
Across a span of 13.8 billion years, the universe has transformed immensely. From its infancy as a hot, dense sphere of almost uniform matter to a sprawling, star-studded expanse where stars and galaxies cluster together, creating a cosmic tapestry of unimaginable scale. These stars we see today, they're a bit different from their primordial counterparts. The stars forming now are crafted from material that was once within older stars, unlike the early stars that were composed purely of hydrogen and helium. And each time we observe a star, we gain insights about the universe's history until the moment that star came into existence. It's like time travel, don't you think?
That's a fascinating concept, but what's so unique about these early stars then?
Well, the interesting part is that these early stars were pristine, formed mostly from hydrogen and helium alone, the material that existed shortly after the hot Big Bang. And when these stars died, they gave rise to the next generation of stars, possibly from a single massive source.
So you're saying there could be very old stars out there with strange compositions?
Correct. There might be old stars with highly unusual element ratios compared to the more common varieties. And we've found one such star that's helping us rewrite our cosmic history.
That's J0931, right? The star you mentioned earlier.
Exactly. This star's discovery is a testament to the tumultuous and ever-changing history of stars in our universe. From the earliest stages where there were no stars, just protons, neutrons, and atomic nuclei, to the formation of the first generation of stars composed of hydrogen and helium. And when these first stars died, often in stellar cataclysms like supernovae, they returned their material to the interstellar medium. The result? The stars we see today. This ejection and mixing of material with the remainder of the interstellar medium is essentially a cosmic recycling system at work. The stars form out of this now enriched interstellar material, each generation growing more progressively enriched with time. Take ESH2106, a star-forming region that showcases a fascinating set of phenomena, including illuminated gas, a bright central star, and blue reflections off of gas that has yet to be blown away. The various stars in this region likely come from a mix of stars of many different pasts and generational histories, but none of them are pristine. They all contain significant quantities of heavy elements.
So that's how stars evolve over time. But how do we learn about early stars then?
Great question. We have two options. We could look to the greatest distances possible and try to detect the earliest stellar populations right when they were in the process of forming. Or we could look around us, nearby, at the oldest, most pristine relic stars we can find, and try to learn what the universe was like at the time of their formation by examining their properties today. The JWST era has given us an incredible wealth of data about the early universe. Yet only in a few rare instances, such as the stars Queeler and Arundel, can individual stars even be resolved at all.
I assume looking nearby offers more advantages?
Absolutely. Looking nearby has huge advantages from an observational perspective because of the level of detail we can measure about that star. Instead of general properties of a population of stars, we can make detailed measurements of individual stars themselves. And in general, there's one specific property we can measure to determine whether a star is more pristine versus more enriched by the elements that make it up: metallicity. In astronomy, any element that's heavier than hydrogen or helium is termed a metal, including non-metallic elements like oxygen, chlorine, and even heavy noble gases. We usually compare the metallicity of a star to that of the Sun, examining the ratios of elements like iron to hydrogen or oxygen to hydrogen. Now, speaking of metals and stars, it reminds me of a recent event. I was out stargazing and I saw a bright twinkling star. It was in the center of the Milky Way, where the most enriched stars are found due to the numerous previous generations of stars that have lived and died there.
Coincidentally, I had a similar experience, but with a difference. I was stargazing too, but the star I saw was towards the outskirts of the Milky Way. That area is home to the most pristine stars, where the fewest generations of stars have formed.
Isn't it fascinating how the locations of these stars shed light on their history? It's like looking at footprints in the sand. And this brings me to an interesting point. We've mapped out stellar metallicities as a function of their location in space. We've even color-coded a map showing the heavy element abundances of more than 6 million stars within the Milky Way. The red, orange, and yellow stars are all rich in heavy elements and should have planets. Green and cyan-coded stars should only rarely have planets, and those coded blue or violet should have absolutely no planets at all.
Wow, the universe never ceases to amaze me. It's incredible to think of the vast number of stars that are being surveyed, each unique and with its own story to tell.
Absolutely. Technological advancements have allowed us to push the boundaries of our astronomical knowledge to new, unprecedented heights. We now have the ability to survey the properties of hundreds of thousands, even millions, or in the case of the European Space Agency's Gaia mission, more than 1 billion stars. It's a marvelous time to explore the cosmos, don't you think? The Sloan Digital Sky Survey, or SDSS for instance, has been observing large areas of the sky for 2 decades, and one star it identified, J0931, really stands out because of its unusual properties. It was first identified by SDSS-5 Milky Way mapper data, designed to measure and analyze data from around 5 million separate Milky Way stars.
Interesting. What's so unique about this star?
Well, J0931 was initially flagged for having a low metallicity, meaning a very low abundance of heavy elements. The amount of iron in the star, relative to the amount of hydrogen, is only about 1.7% of what we find in the Sun. That's a low abundance of heavy elements, but not quite pristine. This piqued the interest of astronomers who followed up on it with the large and powerful Magellan telescope, which has a diameter of 6.5 meters.
And what did they find?
They found that the elements within this star didn't exhibit the typical abundances we normally find in stars. Some elements like strontium, yttrium, manganese, nickel, and zinc were greatly abundant compared to iron. But other elements, such as sodium, titanium, scandium, and barium, showed tremendous deficiencies compared to other typical stars. It's like a stellar cocktail with a unique mix of ingredients.
That's one way to put it and makes it easier to grasp. It's amazing how much we can learn about the universe from a single star.
It's almost as though this star, J0931, is telling us multiple different cosmic stories at once. All stars aren't enriched uniformly. Some stars are partially enriched in certain elements and partially deficient in others. This kind of reminds me of the time I tried cooking a new recipe and underestimated the ingredients. I ended up with a dish that was rich in some flavors and deficient in others.
Ha! Coincidentally, I had a similar cooking mishap too, but it's fascinating to think of a star in such a way.
Absolutely. Now, even if there are multiple contributing factors to how the star obtained the properties it displays, there's only one cosmic story that led to its existence. Astronomer Alex G. and his collaborators suggest that this star formed very early on in the universe's history, from nearly pristine material that had been slightly enriched. But close by, a lone, early, and asymmetric supernova event occurred. This irregularly seeded the interstellar medium, with some elements becoming preferentially enriched in certain directions over others.
So this would mean that stars formed swiftly from this irregularly enriched and recycled stellar debris, a little like making a recycled art piece from the leftover materials of a previous project.
Exactly. And these stars, like J0931, were not formed from a well-mixed sample of the interstellar medium, but from an unusual sample with some enrichments and some deficiencies over the cosmic average at the time. But the reason so few stars display properties like J0931 is because, over time, things change. But that's a topic for our next segment. Now, ejecta from various cataclysmic events, even highly asymmetrical ones, will eventually become well mixed with the rest of the interstellar medium over time.
So it's like a cosmic blender mixing everything up?
Exactly. Most of the stars that form in the universe do so in the aftermath of many violent events, and also form in preferentially enriched areas of the universe.
Okay, so the universe in a way recycles itself constantly?
Yes, and even initially pristine regions that have never formed stars over time will get mixed up with the recycled polluted material.
That's fascinating. But what about this star J0931?
Well, there's only a brief window of time where these heavily asymmetrically enriched stars can form, and only the earliest of these windows will give rise to low metallicity stars like J0931 that also display these properties.
So it's like catching a rare glimpse into the universe's past.
Indeed, and it's only the least massive stars, those less massive than the Sun, which will still persist even today.
So does this star tell us anything about supernovae?
Yes, lesson number 2. Supernova events can produce an asymmetric distribution of elements, and new stars can then form with that unusual distribution imprinted onto them.
Wow, so it's like a cosmic fingerprint.
That's a great way to put it. But the situation gets even more complex. We don't have a supernova model that can predict all of the observed elemental abundances simultaneously. A supernova or hypernova that arose from an about 80 solar mass star could explain many of the elements, but not all of them.
So it's still a mystery?
In a way, yes. Our best models for stellar evolution indicate that stars of between about 40 and 140 solar masses shouldn't go supernova at all, but would rather directly collapse to black holes without a stellar cataclysm of any type. So the story of J0931 is still being told. So it's possible that this star has something new to teach us. Sometimes nature does something different than our naive expectations would lead us to believe. Our simplest models for when stars undergo direct collapse versus when they explode in a supernova do not match up with all of our observations, and will need refinement moving forward.
Interesting. We are still learning so much about the universe and its processes then.
Absolutely. There's so much we still don't fully understand. For example, we observed a star of 25 solar masses simply appear to wink out of existence, with no remnant, cataclysm, or emissions of any type left behind. This is odd because stars of that mass should go supernova, not directly collapse.
That's definitely unexpected. What else is out there that we might have missed?
In the early universe, we have evidence from observed black holes that there are probably clumps of matter in the 10,000 to 100,000 solar mass range that simply collapse to form the seeds of supermassive black holes without any sort of intermediate stage where they formed stars.
So our understanding of the universe is constantly evolving.
Indeed, our present understanding of stellar lives and deaths, particularly at high masses and in the more pristine past, may be far too naive and requires significant refinement. Perhaps much of the astrophysics behind the massive objects created in the early universe is determined by factors we have not been modeling correctly.
And J0931 is a part of that refinement.
Yes, in fact, identifying J0931 and hopefully more stars like it is truly shining a light onto how heavy elements were created at incredibly early times in our cosmic history. This brings us to the final lesson for today. By identifying the oldest, lowest metallicity stars and measuring them with high-resolution spectroscopy, covering a wide variety of elements, we can learn lessons about how nucleosynthesis worked in the most massive stars from the early universe.
So, studying these ancient stars like J0931 helps us understand the early universe better?
Absolutely. It's like having a window into the past. These findings bring us closer to understanding our cosmic roots. Each star, each event, each particle in the universe has a story to tell, and it's our job to learn how to listen.
It sounds like there will always be more to discover.
That's the beauty of space exploration. The universe is an ever-unfolding mystery waiting for us to unravel. To sum up, we've delved into the fascinating discovery of a unique star in our very own Milky Way, known as J0931. This star is rewriting our understanding of cosmic history, with its unusual composition giving us a glimpse into the early stages of the universe. The star may have formed from a mix of enriched and deficient material, a notion that challenges our current understanding of stellar evolution and supernovae. It's clear that the cosmos still holds many mysteries for us to unravel.
It's like finding a rare gem in our cosmic backyard. It would seem that the more we learn about the universe, the more questions arise. And that's the true beauty of scientific exploration, isn't it? I hope you enjoyed today's episode and found it as enthralling as we did.
Absolutely. We'll keep venturing into the cosmos and bringing you the latest and most fascinating discoveries.
And folks, remember, every like, comment, and share supports our journey into the cosmos. So don't forget to blast the like button and share this episode with your friends.
Thank you for joining us on this cosmic journey. Until next time, keep looking up.
Goodbye, everyone, and remember, the universe is full of wonders waiting to be discovered.
This enlightening discovery was highlighted in the article titled 4 Unexpected Lessons from the Milky Way's Weirdest Star, authored by Ethan Siegel on Big Think's site, published on January 11, 2024. For anyone interested in a deep dive, the full URL is in the video description. And now, it's time for me to sign off.